Hi, my name is Abigail, and this is my A2610 digital sampling lab. So here's my prior to week 2 data, where we had to listen to 11 audio tapes, find their waveform identity, their peak amplitudes in hertz, and their peak power in VRMS, which is recorded here. So for week 2, for our supplemental questions, we examined complex waveforms and interpreted power spectra with ampular modulation, a triangle wave, and we looked at a triangle and a square wave for this part. With ampular modulation, we found the period of the wave and the frequency. We also did this for the triangle wave. For AM, it doesn't show this frequency at any of the frequencies I had written down. The period one represents the overall repetition of the waveform, which can be much lower, and it describes how long it takes for the entire pattern of the waveform to repeat. But with the triangle wave, it matched almost perfectly with the inverse relationship, f equals 1 over t. And looking at both the triangle and the square wave, the triangle wave appears to have more power at higher frequencies, which kind of goes against what I would have thought because the triangle wave has smoother, more linear transitions, which requires fewer high-frequency components, meaning less distance travel at the peaks. Then we also examined quantization error, which basically means when we lowered the volume, we found the relationship and noticed that amplitude decreased, but period and frequency remained the same. So looking into other things, we explored record length and sampling rate and the effect that has on power spectrum. First with the 4000 sampling rate with record length 4S, 10S, and 14S, and then a sample rate of 8000 with record length 4S as shown. Then we observed aliasing with tape number 9, sampling rate at 5000, increasing by 2500 until we get to 25,000 and plotting the first 3 peaks of frequency. Then we examined noise with tracks 7 and 8, which we determined were both white noise, and did the peak power over the peak noise. Got 5 for track 7 and 9.7 for track 8. And these were white noise because the amplitude remained the same. So for when we looked at low pass, we looked back at track number 9, and I chose 4000 Hertz as my cutoff frequency because it was where a sine wave appeared, and the filter frequency at 10,000 Hertz, it became more of a straight line. So prior to week 3, we also did microphone validation, which my steps took and frequencies chosen are shown on this slide. So my experiment was fan noise. So for my experiment, I focused on fan noise. I have to have fan noise to fall asleep at night, and I was curious to see if there's a real waveform difference between my dorm fan, my box fan at home, and the fan app on my phone, because the fan app on my phone just doesn't cut it. I can't sleep with it. And to record the data, I used the same process as on the last slide. I just recorded the data for each fan, reduced it, and compared it. The only complication I had in this experiment was putting the microphone in the perfect spot to capture the most accurate noise waves. And some conclusions I had from this experiment was because there are different mechanisms in each fan or generation of fan noise, they do have some different peak voltages and frequencies, but overall the waveforms for the white noise appears the same. So looking at the graphs here, you can see the time history graphs, time versus voltage. If you notice on the y-axis, they're kind of similar, like pretty similar in the 2.5 range to 2.6 range, but they have different numbers of peaks, and the peaks occur at different times. And then looking at the power spectrum, this is the most interesting thing to me about the experiment. Looking at it at first, you can't really tell anything having the first 2 points on there, other than the fact that they all kind of have a peak with 0 at 3 VRMS and then 1.5 VRMS at 0.2. But if you exclude the first 2 points, you can see all of this new information. And with the dorm fan, we can see that there are more peaks, more noticeable peaks further on in the frequency. So around 2000, you could see a noticeable peak, around like 3500, just before 4000, probably around 4300, around 5200, somewhere in there. And then for the fan app, this was very interesting because we have a major peak, which you can almost see on that first graph at 2000 Hertz, which I thought was super interesting. And then for the box fan, it's just a lot more noisy. Like, it's very dense. The graph is very dense. And so I just think that These different things were very interesting to look at, but as you can tell, their peaks are, for the Dorm fan and the Box fan, the peaks were around the same. The Box fan was a little bit higher in the beginning, but the overall peaks were kind of close. The Box fan is just more noisy, and the Dorm fan does have some more significant peaks, which aren't very high, but the fan app has a major peak at 0.2, and then we see some smaller peaks as time goes on, and it is also noisy after that. Of course, they're all noisy, but these are just some interesting things that I took away from this. I would say it was a success because I was able to see some differences, and this was just really great for me. But here is my lab notebook. Thank you for listening to my presentation.